Okay, today's new concept is phase diagrams, and phase diagrams are a way to represent various phases of a substance and the conditions under which each substance exists. Typically we use a plot of pressure versus temperature, so let's write that down here. Temperature, pressure versus temperature. And the lines on the diagram, which we'll show in a few seconds, represent conditions T and P under which a phase change is at equilibrium. That is, that the point on the line, there is possible for 2 or even 3 phases to coexist at equilibrium. Right? Equilibrium means steady state. Other regions of the plot, there's only one phase that exists in equilibrium. So let's look at one of these plots and show you what I mean. Okay, here's a typical phase diagram for water, or H2O. And there's a couple of features I want to show you here real quick. Feature 1 is that, as you can see on the diagram, we have 3 different colors, or 3 different shades of color, representing the 3 different phases of water. There's ice, which is the solid phase, water, which is the liquid phase, and vapor, which is the gas phase. And typically, when you do this, you're going to have the solid, liquid, and then gas. And if you look at a phase diagram that looks a little bit different than this, you're going to know that you go from solid to liquid to gas typically on a clockwise rotation for the phases. So you're going to start here, and go clockwise and go solid, liquid, and gas. Okay, so that's for that part. So now what we're going to do is understand what's happening on each one of these phase regions. So let's look at where each one is. So for example, I said to you that the solid phase is going to occupy this area of the phase diagram, right? So that's all. Anything in here, when we have a point, is going to be a solid. And then here's our liquid phase. This will be anything in this part of the curve or the graph is going to be a liquid. And then anything else here is going to be our solid, our vapor phase. So let's anything up to this area is our vapor phase, right? So if you have a condition, what I mean by condition is a pressure and temperature, where you fall here with the curve, so you read this way and this way. So here's my pressure and here's my temperature. This region here would be a one phase only, and that would be the gas vapor phase. So let's erase all this and show you what the specific things that we just talked about were for. So our equilibrium line for between ice and solid will be on this part of the curve, and as we said here, so here's our this is our equilibrium line between ice and water. So water liquid and solid water, or solid H2O, which is ice, and liquid H2O, which is water. And anytime you're on this part of the curve here, you have both phases in a coexistence. So you have both the water phase and the ice phase. Okay, so you have to be exactly on the line, though. Anytime you're a little bit to the right of the line or to the left of the line, you're going to be only in one phase. All right, and the same thing can be applied to the other regions. So here's our region where we're having a equilibrium between our water phase and our vapor phase. Right, anytime you're on this part of the line, this line here, you're going to have both water vapor and water liquid. And the last thing that you're going to see is the region here where we have a coexistence of both water vapor and solid, right? So unusual to see this in normal every day for water, because normally when we melt ice we go right to water, but there are conditions of temperature and pressure where you could, quote, sublime ice and go directly from solid into the vapor phase, right? And anytime, again, you're on this line here, you have a coexistence of both solid water or ice and vapor water, which is, basically steam. Okay, so there's another couple of other quick points that I wanted to tell you about on this particular curve that are unique and are unique to most of the substances on the planet, right? Not all of them have this, but most of them do. And one of them is called the triple point, and that's located right here. And you can see, let's erase some of this stuff here real quick. You can see that the triple point is the intersection of all those lines. So we have our intersection of this line here, we have the intersection of this line here, and then we have the intersection of this line here. So where they meet is called the triple point, and that's where all three phases at once coexist. So you're right on that dot. And for water, that exists at these conditions here. 0.01 degrees C, and if we read off the pressure, 0.006 atmospheres. So quite a low pressure and a little bit above the normal melting point for water, which is 0 degrees C. Okay, so let's look at some other quick things here. So that's the triple point. And the last critical thing here, or actually the last feature of this particular curve, is what we call the critical point. And that's up here. And you can see here, above which, the critical point, a temperature above which you cannot discern a liquid from a vapor. In other words, if you looked in the little vial, you couldn't tell you if it's a vapor or a liquid. And you also need a critical pressure to do that. So we'll call that the critical pressure. So that would be this thing here, right? So here's our definition down here. A temperature above which the critical temperature and pressure, critical pressure, it is no longer possible to distinguish between a gas and a liquid phase. And anything above this critical point here, we call that a supercritical fluid. So a supercritical fluid. And they have some unique properties that we won't go into, but for example, CO2, carbon dioxide, you can make that into a supercritical fluid, and they use that in industrial purposes for some extraction things. It allows it behaves kind of like a liquid as far as being able to take out a lot of material, but it also has the ability to flow into a lot of nooks and crannies to get into that structure. So the supercritical fluid technique is often used for extraction purposes. Okay, so let's quickly just do a quick tutorial on how this works and what you can use this for. All right, and so let's do some quick erasing here. So the conditions on which you can do this are, let's say you have you're given a temperature and a pressure, and we'll just use the red pen here. And let's say you start at a condition here, right? And you can read off what the temperature is down here, and you can read off what the pressure is over here, right? So here's my pressure, and here's my temperature. And if you did this right, this is going to be about 0.5 atmospheres, and the temperature, if I'm doing my calculations right here, it's going to be about 15 degrees C, right? So plus or minus 5 degrees C. So at those conditions, half an atmosphere and 15 degrees C, we only have one phase of water, right? Now, what would happen if we took that and we dropped the pressure down to a point where now our point is here? We kept the temperature the same, and we read across to our pressure over here, and we said that that was roughly, I don't know, let's say that was 0.1 atmospheres, right? So we dropped the pressure down to 0.1 atmospheres, but we kept the temperature at 15 degrees C. Well, now you can see that as we drop the pressure, we've increased the likelihood of it going into a vapor phase until we get to this region here. When we get to the boundary here, or the line that separates the water phase from the vapor phase, once we get to that line, we will have a phase change, right? So as we cross over that line, right here, we'll have the phase change, and that phase change conditions will be 0.1 atmosphere and 15 degrees C. Now, we could also say, okay, so now let's move the point here. So let me erase some of this stuff so we don't get confused. So keep an eye on what the conditions were for here. I'll just do it a different color. So now we're going to move our dot to here, right? So we've kept the same pressure at 0.5 atmosphere, so it's over here now. But now if I drop the pressure, I actually will have a different temperature, right? My temperature now is about 50 degrees C. And at 50 degrees C, I don't need as much of a pressure drop, so that might be 0.2 atmospheres, right? So but I'm still on that same line here, right? I'm still on that same line in here. So just by changing the conditions of where your start point and what your end point is, you can change what the conditions are to go into the next phase. So let's just look at that one more. Let's look at that a little bit more closely with a specific thing here. So again, let's use our red dot, and we're going to start here, right? And it's telling me if I reduce the temperature and stay the same pressure, right? So I'm staying on the same pressure line here. If I reduce the temperature, I'm going to go from the water phase into the ice phase, or the water phase, liquid phase into the solid phase, right? However, if I do reduce the pressure, so I'm going to go this way, and I keep the temperature the same, so here's my temperature, right? If I go this way, then I do not go into the ice phase, I go directly into the vapor phase, right? So you can manipulate your material by changing the pressure and temperature to determine which phase you want to go into or out of, right? But the normal 1 atmosphere is what we've all been accustomed for water, is if we start here and we add heat, right, that's our temperature, we're adding heat, the normal progression is to go from solid to liquid to gas, right? That's the normal progression at 1 atmosphere. You have to be at 1 atmosphere. But if you were down here, let's say at something like 0.003 atmospheres, and you started here, the next progression would be, instead of going from directly from, let me erase some of this, instead of going from directly from solid to liquid to gas, you would actually go from, and here's our starting point, you actually go right into the vapor, solid to vapor, which would be called sublimation, right? And there are materials that do that at temperatures and pressures that are more normal to what we normally live at, which are, minus 10 degrees C up to about 50 degrees C, and pressures which are, about 0.8 atmospheres up to about 1.1 atmospheres. And that would be a material like CO2. CO2, dry ice, you've seen that before. You take the solid pellets of dry ice and you put them on the floor. They don't turn into liquid CO2. They go directly to gas. Okay. All right. So one more quick thing about the curve here, and then we'll be done with the tutorial. So let me erase some of this other stuff. So I'm going to erase this and show you how this curve is used in everyday life. So many of you have heard of freeze-dried food, right? And let's see how that works. So when we talk about freeze-dried food, fruit comes to mind, right? And we're normally operating at the 1 atmosphere thing. So normally a freeze-dried food at room temperature, here's where our food would be at room temperature as far as the water content, right? It's around 20 degrees C. Maybe it's a little higher. Let me just move this a little higher, right? So maybe it's up around here, right? And this is roughly 20 degrees C, right? And that would be our temperature. And our pressure is defined as 1 atmosphere, right? Now, there are a couple of ways. Let's say you wanted to remove the water content in food. And this all came about in World War II, where they had to ship a lot of blood to the soldiers overseas. And, blood is mostly water. And so they wanted a way to reduce most of the water or eliminate the water part so they could ship a lot more of it. And so they came up with this process called freeze drying, which is now used throughout the world to preserve food. And what you do is you take the food and you actually will freeze the food at room temperature. So then you will, we're going to show you which way you go. So you're going to go this way, so you freeze the food, right? And the next thing you do, okay, so you have this big frozen food. It still has the water in it. And then the next thing what they're going to do is, so here's our new point now, right? And then what they do is they drop the pressure and they get into this range, and all the frozen water now turns into vapor, and you have this huge open structure because when you freeze something, the water expands, and the vapor quickly leaves the food, and you retain the shape of the food. You haven't made it condensed or densify or anything like that. And then when you go to add more water, right, then it's much easier for the water to reconstitute the food. Well, your question might be, well, so why do you want to do it? Why do it that way? And why not just do the normal way you would think about drying something, which we all do, and here's our starting point again, is to just add heat and drive it off this way. Well, we know what happens sometimes when we add heat. We change the structure of the food. So when we cook food, there's chemistry going on, and we can actually break down the materials that make the food up, all the carbohydrates and the fats and proteins and all that. And if we add too much heat, we actually change the content of the food and the taste and all that. And then the other question, so that wouldn't be a good way to preserve the food. And then the other way you could say is, why not just let the water evaporate naturally, right? Because we've talked about evaporation before. And what happens there is, as the water evaporates slowly, first of all, it takes time, and then the food can decompose that way. Or, as the water evaporates slowly, what happens is the tissues in the food slowly densify, and you get something that looks very dense and very hard to reconstitute. So think of a very dried out raisin that's gone through that process, right? The dried out raisin, if you add water to it, which raisin is mostly loss of water from a grape, it doesn't densify easily. It doesn't reconstitute easily. But if you freeze dried the grape, you could get the grape back easy. So that is why freeze drying works, right? Because if we went this way, we can destroy the food. So if we went this way, we would destroy the food, possibly. But to get into the vapor phase, which is where we want to go to dry off the thing. But if we go this way and then this way, we can do the same thing and preserve the food. So that's the lesson on the phase diagram and reading a phase diagram.